Hello, my name is Chen. I'm an undergraduate student majoring in mathematics with minors in biology and computer science. This project is about estimating hazard rate with censoring a measurement error. From the lung cancer data containing the patient survival time, which is defined as the length of time from diagnosis of cancer to death, we can estimate hazard rate of lung cancer. However, there is always some measurement errors in the observed survival times. Also, censoring is another problem as 63 out of 228 subjects left the study early or they were still alive at the end of the study. We do not want to exclude these censored data points since they can still provide partial information about the survival time. A lot of statistical methods have been proposed to address only the measurement error issue or address only the censoring issue. In this project, we would like to consider both issues at the same time for our hazard rate estimation. First, we consider a convolution model where the true survival time z is convoluted and hidden in the observed survival time x with measurement error e, and e follows a normal or a double exponential distribution. To handle the censoring part, we define another variables w and delta in equation 2. Our goal is to formulate estimators for hazard function of the true survival time z based on censored observations of w and delta. Then we can apply such estimators to model lung cancer hazard rate. To construct our estimator for hazard function, we start with an estimator of probability density function, or PDF, proposed by Zhu and others. The deconvolution kernel density estimation and inverse probability of censoring weighting methods were adopted to handle the measurement error and the censoring parts respectively. Then we formulate an estimator for the survival function by integrating the PDF estimator. Finally, we can construct a hazard function estimator, which is a ratio of the PDF estimator to the survival function estimator. Now, we are ready to apply these estimators to the lung cancer datasets. In Figure 2, we propose a lung cancer survival rate model, where we can see the survival rate on the date of diagnosis is really high, but around 300 days after the original diagnosis, the survival rate drops by half to 0.5, and the survival rate approaches to 0 after 1,000 days. Usually, patients will want to know conditional probabilities, such as given that they are still alive, what are their chances of death in the next year? To answer this question, we can refer to the hazard rate model in Figure 3. According to our model, the hazard rate increases rapidly after 800 days since diagnosis of lung cancer. Next, we conducted simulation studies to assess the performance of our estimators with different sample sizes based on simulated data following a Weibull or a gamma distribution. This way, we can compare our estimated survival and hazard functions with true survival and hazard functions. Our simulations suggested that our estimators perform well even with a sample size of 200, which is comparable to our lung cancer datasets. For the last part of this project, we discussed the case if we estimate hazard function based on observed survival time x rather than based on survival time z. We compare these two estimations in Figure 6, where we see the effect of measurement error resulting in two different models. In the future, we would like to construct confidence band to conduct more statistical inference based on our estimators. In addition, the estimators we presented are examples of kernel methods, which played an important role in many machine learning algorithms. One challenge of using these methods is to find the optimal bandwidth h, which controls the smoothness of the curves. We would like to develop better bandwidth selection criteria for our estimators in the future. Finally, we want to highlight that there are many other applications of our estimation method. We can also consider hazard rates of, for instance, menopause age or remaining useful lifetime of a machine, as long as it fits the time to event setting similar to the lung cancer data we explore. Thank you.